So circles, what would the world be without our circles? I'm trying to picture like a car with those square wheels, you know, like we wouldn't get there.
You can do ovular wheels.
What? I don't know if we can have the oval without the circle, right? We need this. No, we can't. So we're going to learn. Are we done? So we're going to take the limit of number of sizes and goes to infinity, and that's a circle, right? Anyway, circles are good. Just remember that when we're up to like 20, 50 euros. Circles are good. So here's the definition of a circle. Did they tell you that in kindergarten? What did they tell you in kindergarten? Circle, it's this thing. What did they tell you in kindergarten?
Like this.
And that's what it is. Here's what a math definition of a circle is. It's a set of points equidistant from a common point. And we call that common point the center. Right? You ever have the dog? They're so smart, right? I'm going to run after you. And they pull on their little thing that they're tied up with. Right? And they go all the way around. And the dog's dumb. But we're smart. We get this, right? My cat will be happy. All right, so a circle. Picture the dog. He's pulling up the chain. He's trying to run after the mailman, and now he's in circles. So that's what a circle is. We call it by its center point. So if we call the center point A, this is a circle. A radius is the official definitions now, the segment whose endpoints, one is the center and one is any point on the circle. So I can draw an infinite number of radii just by finding all the points on the circle and connecting them. A chord is also a segment in a circle. The endpoints are actually on the circle. And a diameter is a special kind of chord. It's a chord where, see, the endpoints are on the circle, but it goes through the middle, through the center. That is a diameter. Official definition, I know you know what those things are, but the official definition, chord that goes through the center, radius is a segment whose endpoints, center, and endpoint on the circle. More definition, a secant. A secant is a line, and it intersects a circle in two places. So this thing here is what we call a secant. A tangent is a line that intersects the circle at one and only one point. We call that point where it touches the circle its point of tangency. We've heard the word tangent before. It is related to the tangent that we've learned about in trig. You will learn more about how they are related when you learn about trigonometry for reals, more than just right triangle trig. So it could be next year for some of you, it could be in 2 years for some others. We have three places you can be relative to a circle. You can be on its interior, so you're inside. You can be on its exterior, so you're outside. Or you can be on it. So that's like this point. You're on the circle. Those are the three places you can be. A concentric circle. These are coplanar circles, so we're all on the same plane, nice and flat. And it has a common center, so the centers are the same. Concentric. So you can have kind of an infinite number. You put one, you have one, right? They all have the same center. Alrighty, so let's just prove a point here. So here's the figure, and it's on your little picture here, kind of middle-ish. I want a name of a radius. Jerry, give me the name of a radius.
AC, all
AC.
four distant lines.
What?
All four distant lines.
This?
Points.
This is not a radius.
No. I'm saying that all four distant lines. Because,
well, a chord is a segment, and a secant line is a line. That would be the difference. But yes, it's like you took a chord and you stretched it out. So a radius, AC, what else? We got another radius on here. Yeah, what else? A Christian? BC, so, I mean, I employed AC, but, you know, BC is one also. Whoops. CB, CA, you can call it that. Name a diameter. AB is a diameter. We could draw other ones, but that's the only one that's showing. Name a tangent line here. Tangent line? Tangent line? Really? Really? Go ahead, Romy, what's a tangent line here? ED, okay, that one, I think I called it, yeah, I called it ED also. You could call it BD, ED, right? Anything that identifies that line. Name a secant line. Secant? Hey, buddy. Yeah. AG, that's my secant line. Name a chord. Name a chord. Christian? AG, you have another too? AB, right? By diameter is also a chord, so AG and AB, they're both chords. Name the center. Where's the center? C. Yeah, not a trick question. Name a point on the interior of the circle. Christian. C. Name a point on the exterior of the circle. Ravi. E. Got any others? E. Right, we got a few different ones. Name a point on the circle. Jack. Hey, what else? E. E, right? We get it, right? Yeah. After that factoring thing, this is nothing. Yes, sir. A secant is a line that intersects a circle at 2 points. Okay, so this did not come out very well on your paper. None of those little graphing lines came out, so you're going to have to look up here. So find the length of the radius of circle A. Thomas. 3. Be careful, always look at the scale. So each box is 1 unit, so it's 3 units. So then what's the diameter, Christian? 6. What's the radius length of circle B, Jack?
2.
2 boxes. And so what's its diameter? 4. This is easy. That's really hard. No, it's not hard. That's it. It's easy. Okay, let's talk about coplanar circle intersection. Oh, no, this is harder. No, it's not. So if you have 2 circles in the same plane, or more, I guess, how many points of intersection can they have? So here's what it looks like if you have 2 points of intersection, right? Something like that. If you have 1 point of intersection, it could be like one inside, or they're both on the outside. That's 1 point of intersection. No points of intersection. Either they're not touching, or they are concentric. Because concentric circles will not touch, right? They have the same center. So these are different points of intersection looking at circles. So with these points of intersection, we can talk about common tangents. And a common tangent is one line that's tangent to more than one circle. So for example, here are 2 circles with no points of intersection, and I can actually draw this line so that it's both tangent to this circle and that circle. They have this tangent in common. It's the same line. Same idea here, you can have the same point, same tangent line works for both circles. So, common tangent. So the idea here is, can we figure out how to draw common tangents for each set of circles? Like, for example, where might I put a common tangent for this guy over here? This is on the bottom of the page here. Mons, where could I put one?
Across the top four.
Right, so I could do something like this right now. This little drawing tool I have is probably in this. Yeah, not too bad. All right, that's meant to be straight. Right, so I can have a tangent line going that way. Can I have any others? Yeah? Oh, I can have one that goes like, oh, okay, so it's going to go here, and then it's going to touch that one too. That's a pretty good one. What else? Yeah? The opposite, like one going this way, right? So now it's kind of hitting that one going this way. Oops. Yeah, that's meant to be straight. And this little tool not so good. And then Robert, where's there another one? Yeah, kind of like mirroring almost that one on the top. So how many like tangent lines? Are there any others?
No.
Do you think there's another one? Yeah?
We have more diagonal.
But then it won't touch, right? I think there's, because remember, there's 2 points, right, that we want. I don't think we can get another one in there that's going to touch. Because, think about it, like if you tilt it, it's not going to hit the other circle. So let's see. I think we can get 4. Let's look at this middle one. So let's see. How can I draw common tangents for this one? Let's see. I'm looking up to this part. Now I can't see the people behind me using their hands. So what you guys? I can't even see you guys. What can I pull on? Where can I put a common tangent? Just like we did here. I want one line that's going to touch the circle, 2 circles. On the edge, right? They don't want to intersect past more than 1 point. Like right in the middle of that. Right in the middle, like this? Yeah. They're assuming they're touching at one point, I can draw that line right down there. There's one. Where else? Is there anywhere else? Where else? Where, oh, come on, friends. Yes, where would I put it? Across the top. Yes. Do it for me. And draw where's the other one? Well, I think if I do a diagonal, I'm going to get more detail. It's just going to take more than one spot like on this circle. But I want tangents. I think that's the best we can do. Okay, and now they're kind of intersecting. Yeah, across the top, and then also across the bottom. I think you only get two. Oh, okay, there we go. What if it was something that looked like this? You just get one, right? I think that's the only one, because it only meets in one place, so I can't understand it any other. So there could be other configurations, but the idea between this common tangent is trying to figure out how you can draw them. So there we go. That's an example of that. And now we're getting to our first circle theorem, which means we're going to take out that little circle theorem thing, this one, right? We're going to go find that little piece of paper. And since it's our first one, it should be right here. Hopefully they match. Right, so you have that paper. And it says, in a plane, a line is tangent to a circle, if and only if. So I got this going, right? It's a biconditional. If and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. Right? And they are like a mouthful. First of all, you need the picture. So when you're doing this thing, it's like, I need the picture. So like draw your circle, doesn't have to be perfect. And think about what it's saying. So like if you have a radius and a tangent, next to your tangent, it must be that this is perpendicular. And if you have a perpendicular, then it must be a tangent and a radius. That's the kind of the if and only if. So this is where the little illustrations will be important, because sometimes reading these things, if they're not really easy reading. So keeping a picture is my hope for you to kind of remember. Okay. Okay. So examples with this. So I want to verify that line BC, oh, that's this thing, that it's a tangent to circle A. How can I verify that this thing is a tangent to circle A? Yeah, I think so. What I heard was, look at triangle ABC. Does A squared plus B squared equals C squared? And 6, 8, 10. Oh wait, I can reduce that, right? That's 3, 4, 5 triangle, right? That's one of our triples. So this must be a right angle. And if it's a right angle, this is a tangent, that's a radius, right? And we can see it's a radius because there's the center. You're allowed to, if it looks like the center and it says A, that's the center. And so that's true. And just for fun, does it work the other way? I mean, it better, right? You know, it seems like it would have to. Is this another triple? 8, 15, 17. And if you're not sure, you want to just put it in your calculator. Whoa. No. Okay, so clear that. So you can just do square root of 8 squared plus 15 squared. And if you get 17, we do, yes. I check them both just in case it was a little wacky, but yes. Huh? Oh. What? How do I know it's a right angle? It could be. I don't know. I don't know. What? Oh, I see what you're saying. Right. Geometric mean works if I know this is a right angle. I don't know that.
So 2.
But I don't need it in this case. Right, there's that times that square root. Oh, that's nice to remember that. That's cool. But I think we don't have enough information to know it applies here. So by the Pythagorean theorem, these are right angles, so it must be a tangent. Yes, sir? No, you would write verified. Since the Pythagorean theorem shows us that they are right triangles, then whatever angle that is, then angle ABC is a right angle, therefore CBC is 18. And then I'm just using that theorem that we just learned. Because it's a right angle, it must be a tangent. Yes? This one? Yeah. Oh, you want to find the angles?
No, you can probably figure it out.
You can definitely figure it out. You can use like inverse tangent, inverse sine. Yeah, we could use the inverse trig function if you needed those angles. We sure could. Right, so you're saying, well, maybe they are 45. Let's try and find it out. All right, let's try this one. It said given B is a point of tangency. This is a point of tangency, which means that's a tangent. Find the radius R. Well, if this is a point of tangent, it means that this must be a right angle. So I'm going to put in my right angle. And so now what do I know? A squared plus B squared is C squared. So we're just going to write that out. So I'll start with this one. R squared plus AB squared, right? This squared plus that squared is this whole thing. Now be careful. What is that whole thing? This piece is R and this piece is 50. So what is the length of the hypotenuse? Using the segment addition postulate. Yes? Well, that would be multiplying. So what's it going to be? What is it going to be? 50 plus R. And I'm going to just write it as R plus 50. You can write it as 50 plus R. So that means that this square plus that square is that squared. When you square your C, make sure that you're grouping it. Because it's this whole thing square. Agree or disagree? Does that make sense? I'm just using Pythagorean theorem. So now we have to expand this a little bit. Awesome. Okay. So R squared plus A squared, oh, let me just write that, 6,400. If you're writing R squared plus 2,500 right now, stop. Remember how you square a polynomial, especially a binomial. Expand this out. Remember our friend FOIL? We just talked to our friend FOIL, right? So you have to do the first, or just do the distribution twice. Just do it that way. R times R. R times 50. Then in the insides, right, 50 times R, and then the outsides, and combine those like terms. So don't forget the OI. Outsides and insides. So this is going to be R squared plus 100R plus 2,500. So you see how these things can become quadratic real quickly? Look at that, quadratic. Hey. Oh no, this one, I can subtract out the R squares, can't I? Oh, now it's not quadratic anymore. That's not fun. Now it's just easy. Right? You saw what we did here? Right there, they cancel each other out, those R squares. So now, what am I going to do? Oh yeah, so I have to do 6,400 minus 20. So what is that? 3,900? Is that right? I think so. And then to find R, I'm just going to divide by 100. So R equals, looks like 39. Now I'm just checking. Is that what they asked for? Yes. Find R. They could say find AC. So be sure you're reading the question and answering the question. What is AC? 39 plus 50. So make sure you're answering what they want. Makes sense, not make sense. Raise your hand, makes sense. A whole bunch of people haven't raised their hand, doesn't make sense. So you have to ask a question. Oh, now we have to go ahead. Okay, good. All right, we have another theorem. So, tangent segments from a common external point are congruent. So, these are common external point, S, and these are tangents. Oh, wait. If they're tangents, that means if I draw a radius to them, this would be a right angle, right? So by doing that, I think it's helping us see in the picture that these are tangents. So when you're drawing your picture here to kind of represent this theorem, I would, you know, here's my center, and maybe do this bit too, to just show that you've got these. And what about them? These will be congruent. The tangent segments will be congruent. So let me look, my drawing's terrible. So I'm going to put it here. So those will be congruent. Okay, that's the whole theorem. You draw a little picture? Have I drawn a little picture? Oh. Where's your little picture? Oh, you did. Wow. Okay. They're looking good. So let's apply this theorem a little bit. Just a couple of examples. So for example, given RS and RT are tangents. So if you ever want to kind of mark that they're tangents, I would just do this. Okay, you draw. So that way you know by looking at the picture, those are tangents. Find X. Well, it must be that these two things are congruent because they're coming from the same point, so that means I just set them equal. So solve that equation, X is 8. And again, I go back, you just want X. Okay, I'm done. They might have said find something else, I don't know. So I did. Is it with me so far? Yay. Whose hand is enough? Okay. All right. Let's look at this guy. Well, because I see these little markers here, what do I know about these two things? They are tangents. Therefore, they will be congruent because they're coming from the same endpoint. So that means that x squared is 9. So what's the value of x? Really? 3. And what else? What else? -3. Right? X squared equals 9 plus or minus 3. When you are presented with x squared equals 9 and you want x, you have to give the positive and the negative solution. This is not the same thing as the square root of 9. The square root of 9 is positive 3 only. But if you're solving this equation, it includes that negative solution. So not the same thing. Just so we remind you of that. Don't forget now we have to check do these solutions make sense. So 3 squared 9. Is -3 a viable solution here? And what do I mean by that? Does it work? Is it, is that a problem? How do you know if it's a problem? Yeah? A side can't be negative. So if you were to plug that in a negative side, no. So I do have two solutions. It could be -3. So don't just toss away the negative. Sometimes they work. Yeah. So -3 times -3, 9. Fine. X can be -3. Why can't it be negative? It's not. Square -3, you get positive 9. So it's fine.
Maybe it's not
But he just doesn't like it.
Distance is negative, it's saying the distance is the negative, and opposite the negative.
It could be x, whatever x is, whatever we're doing, it could be negative. It could be -3. X could be -3. And we're on the u tries, really, that's it. So go ahead, work those u tries. While you're doing it, I'm just going to display answers here for classes. So that if you are kind of reviewing this video, you can actually see what I got. I think the graph here is very readable, so I think you can actually see it without these little charts being up. And I'm just putting the answers through just so they're recorded and then I know. Those are the introductions.